We have chapter 1 still. 1 is pretty long, but it's going to be your easiest chapter. So we are on section 1.4. We're going to get through that in 1.5 today. And here we go. So section 1.4, we have definitely, please remember that we've gotten through a couple things. So we know that we have linear equations, how to recognize those. If we have more than one equation, we have a system of linear equations. We know how to represent them by an augmented matrix. We now know a lot of different elementary row operations, and we're trying to get them into reduced row echelon form or row echelon form in order to simplify those systems so that we can solve them. So if we just go through row echelon form, where we follow those first 3 properties, we'll have done just the Gaussian elimination. So it's going down the matrix. If we go ahead and go back up the matrix and get all the way to reduced row echelon form, we have fully completed a Gaussian Jordan elimination. So going both down and up. So today, just realize we're on section 1.4. So we're going to be learning about inverses and some different algebraic properties of matrices. I had asked you to kind of look at some of these tables, so I hope that you have. But also don't forget that up to this point, we are dealing in real numbers. So just realize that, you know, we're not going to get anything too complicated right now, but our real number system, that is going to include our natural numbers. And if you add 0, we've got our whole numbers. Then we have all of our integers if we also include the negative numbers. Then we also have our rational numbers, which includes our fractions. And then we also have our irrational numbers that are going to have ongoing decimal numbers. So just realize that is the set of real number systems that we're working with. So here is going to be all those different properties that you're going to want to know about your matrices. So here we have a lot of these things that you have seen in algebra before, I am sure. So keep that in mind. So we have the commutative law. So I think we've seen that. If we add a matrix A plus a matrix B, that's going to also be the same as B plus A. Then we also have the associative law. That is going to hold. Then here we have the associative law for matrix multiplication. So you're going to want to make sure that you do whatever's in the parentheses first, then multiply it by whatever. Then we have the left distributive law. We've seen this before. We're going to be distributing the multiplication of that matrix A by B and C. Then we have also the right distributive law. So if we brought A over to the other side, we could do B, they would end up equaling B times A plus C times A. We've got this same thing going on for our subtraction. Then we have it here for our smaller scalars that we might be multiplying it by. So you're going to want to have a really good handle on these properties. So please bookmark this as your theorem 1.4.1. So one of the things that I am going to do on your study guide is I'm going to have your different theorems for you. So that'll be nice. You'll have them combined and all in one place. So you're going to want to go ahead and check these because you might hint get some true false questions about your different properties of matrix arithmetic. So here we go. So this one I think is pretty self-explanatory here, but we'll go ahead and look at it really, really quickly. So we're going to look at example 1-4. So let me go ahead and make sure we got our books open. So in section 1.4, this would be example 1. So here you would want to, for instance, another thing I might ask you on an exam is if you have these different properties of matrix arithmetic, can you prove them with actual matrices? So here, what property is this? Does anybody remember from the table I just showed you? If I had to ask you, which one would you say it is? It's on there, right? So hopefully you guys saw that. But hopefully you recognize this. A times the multiplication of BC, that quantity, equals AB multiplied together and then times C. So you can kind of check that out. So let me ask you this. How would you quickly determine what you should get for these? We learned how to do this before. If I asked you, what would be the resulting product here of A times the quantity BC? How would you go through and do that quickly?
3 by 2. What do you do the BC together? That would just give 2 by 2.
Yep.
Shape.
Uh-huh.
We have 3 by 2 times 2 by 2.
Uh-huh.
You have 2 little numbers are inside numbers are the same.
Mm-hmm.
The outside numbers are what's left over. With the shape of the product.
Yeah. So for that whole quantity, what would we get here? We get a 3 by 2, right? Does everybody agree with that?
Yeah.
So that's something that I could be asking you on the exam. Even without calculating all this, what would be the resulting size of that product? So here, okay, if we do BC first, that's going to equal what? How would we go about doing that? It is a 2 by 2. You are correct on that one. So that one's a 2 by 2. So can anybody do that really quickly in their head? So what would that first matrix be? 4 plus. Okay, so be 10. So we're doing 4 plus times 1 plus 3 times 2. So that's 4 plus 6. Then what do we got? How would we do that if we're doing row column expansion? What would be the next thing we'd look at?
4 times 0 plus 3 times 3.
Which would be 9. Okay. Then what do we got? Yeah, you take that second row times your first column. Okay, so we got 4.
The last one, second row of B, so 2 times, and then the second row of C, second column C, sorry. So 2 times 0 plus 1 times 3, which is 3.
Yeah. So does everybody see where that came about? How could you do that a different way? So that was called what? Yeah, that's row column expansion. What is one other way you could do that? Yeah, you could do the column row. So how would you, just if you, for kicks, how would you have set that up if you're going to do column row? So you would be doing 4, 2. So that'd be your column here. And then you do it times 1, 0. Right? And then you'd have plus, what would be the next thing?
2, 3.
You got 3, 1. So that'd be your next column. Then times your second row. And just remember here in this way, you would actually get 2 different matrices and you'd have to add them together. So it's kind of up to you, which is going to be fastest for you. So looks good. Yep, Stephanie's got associative law for matrix multiplication. Yeah, Christopher says a 3 by 2. Yes, that'll be our ending product. Then we got some people doing some calculations for us. So then now that we're done with this, now we can go ahead and do our A. So here we've got our 1, 2, 3, 4, 0, 1. And then we have this by our 10, 9, 4, 3. Anybody want to go ahead and tell us what that ends up being? Anybody want to look in their book? This one is BC. Anybody know what that ends up being?
It's 18. 15,
Yeah.
18, 15.
Okay.
Row, and then 46, 39 on the second row. And then 4 and 3 on the bottom.
4 and 3 on the bottom row. Okay. So you're going to want to go through those steps and make sure that you get that same matrix. So this would be doing row 1 here, 1 by 2. 1, 2 times 10 and 4 here. You'd put that in the first position here. You do that same row again, then times the second column, put that here. You'd keep on going through. You could also do it by your column row expansion. So that's what you end up getting if you do A times the quantity B times C. Then if you did the reverse, you would be doing A and B first. And then you would get a resulting matrix, and then you'd be multiplying it by C, and you should get the same thing, correct? To be able to prove this particular associativity of matrix multiplication. So the second one, you would be doing AB equals this jazz first times your B. Then once you got that, then you'd be multiplying it, your AB times your C, or you could write it preferably the other way. And that should get the same thing here. So you're going to want to prove that to yourself, because what if I put instead of numbers, what if I put variables in those spots as the entries? So you could have actual like different letter entries instead. Okay, so then here's where I wanted you to actually look at that column of different properties, because not everything is going to hold the same as algebra. So here's one example. It says A and B may be defined and BA may not. So what did we learn before? Why would AB maybe necessarily be defined, but BA may not? The what matters? Yeah, the order matters. So don't forget that. So in this case, order is really, really important, because one of them could be defined, the other one might not, depending on the order of this. So if we look at AB, what is that going to be? A 3 by 2? And then we've got a 2 by 2. So that one's going to be defined, right? That one is defined. And we're going to get a, what size are we going to get really quick? 3 by 2. Yeah. What about BA? So if we've got BA, here we got a 2 by 2. And then we've got our 3 by 2 for A. Now what would we say? What? We'd say what? Yeah, we can't do it. It's undefined. Yeah, because the 2 and 3 don't match, right? So that one's going to be undefined. So, but here's where you've got to be careful, because in certain instances, AB will equal BA. Does anybody read ahead and know when that instance is? Well, there is a special instance. We'll see if anybody knows it, but we'll get to it. But in this case, if you're just looking at AB and you're comparing it to BA, order is going to matter, folks. So please realize that, depending on the size of your matrix. Okay, so like I said, we'd already looked at that. So the other thing too is, what if A and B are the same size? And let's just say that both AB and BA are defined. But here's the other reason why order is going to matter, because AB is not necessarily going to equal BA, right? So depending on the order and how you have multiplied this, you're not going to get the same product. So if we looked at AB, so we know both of these are 2 by 2 matrices in either case. So we know that that's going to be defined. That's really easy to look at. But what would AB equal? So this is going to be what? -1. Okay, then we got -2. Right? Then we've got 2 plus 3 times 3. So is that 11? Then we have 2 times 2, that's 4 plus 0. And then we have BA. What is that going to equal? Here we've got 1 times -1 plus 2 times 2. So what do we got? 3. Then we got 1 times 0 plus 2 times 3, so that'd be 6. Then we've got 3 times -1 plus 0 times 2, so that's going to be -3. And then we got 3 times 0 plus 0 times 3, so that one's going to be 0. So check that out. So just realize not everything you have done before in algebra is going to hold true for matrix. Okay, so order here is going to matter. All right, so now let's move on to a new concept here. So here you're going to want to know about zero matrices. I think these are very self-explanatory. What do you notice about zero matrices?
They're all zeros.
They are all zeros, so easy enough, right? So hopefully you guys will, so what do you think is going to happen when you go ahead and add a zero matrix to a matrix A? You're going to, yeah, you're going to get A again, right? As long as what? As long as they're the same size. So in this case, when you're talking about addition of a zero matrix, it doesn't matter what order you're going to put it in. What about this one? If you have A minus 0 equals what? It's going to be A again. So here, B, if we minus a zero matrix of the same size, we just end up with B. Here, what do you think about this? What will you end up with?
0.
Yes, you'll end up with 0 here. So all these are pretty obvious. What are you going to end up with this? Yes, you're going to end up with 0 here because you're multiplying the whole matrix by this scalar 0. All right, so here's an interesting property though. What if you are given the equation that a scalar C times a matrix A equals 0? Well, then you're faced with a decision here. You're going to have to determine whether or not that scalar is the one that equals 0 or if the matrix itself equals 0. So here, just realize this could end up with 2 different options here. So you could have C here could be 0, A could be anything. Or if C actually is some sort of scalar amount here that's non-zero, then you would have to have A as being a 0 matrix. So I think that's pretty obvious as well. So we just ran through those. You're going to want to make sure that you know your theorem 1.4.2. Properties of zero matrices. Those I think you're going to be pretty familiar with. So here is something interesting here. So if we have the instance where you have if AB equals 0, then at least one of the factors on the left is 0. So we know that from algebra, right? If we're given this expression AB equals 0, then we're always thinking to ourselves, well, either A or B equals 0, right? To get that. That is not going to be the case with matrices. So just make sure that you remember this one as well. So with matrices, AB might equal 0, but that does not mean that A equals 0 or B equals 0. So this is like an algebraic expression where you have AB, and we're used to seeing this. But then we use our uppercase letters to denote a matrix. You could get the product of A times B equals, in fact, 0. But that does not mean that A equals 0, B equals 0. And so to kind of prove it to yourself, you can kind of look at this product here. So AB is going to equal, we got 0 times 3 plus 1 times 0. That's going to be 0, right? Then we got 0 times 7 plus 1 times 0. That's going to be 0. Then we got our row 2. So 0 times 3 plus 2 times 0. That's 0, 0. And we got 0 times 7 plus 2 times 0. That's also going to be 0. So as you can see, that product is going to be it's going to be a 0 matrix.
Is there a word for any type of matrix besides zero matrix?
We're going to be going through quite a different, yeah. So those are coming. So this will be a 0 matrix product. However, when you look at A and B, they themselves are not 0. Does anybody notice anything? Can anybody determine or see a trick? Oh, so here's one of those other patterns you're going to want to, but when will this happen? What is something that is interesting about A and B? The column of A is all zeros. The row of B's are all 0. What else needed to happen for this to be a 0 matrix?
2 by 2.
Yeah, they're the same size there. So they're 2 by 2. So just to be having little tricks up your sleeve with looking at these different matrices. So next type of matrices, to directly answer your question, we now know 0 matrices, so they're all zeros. Here's your next type of matrix. You have an identity matrix. Can anybody guess what in the world are the properties of these? They have what? Yeah, so by default, an identity matrix is in reduced row echelon form, right? We also notice that they're all ones along the main diagonal. What else do you notice about the identity matrix? Yes.
It's a square matrix.
It's square. So here's where you're going to want to make sure you know the properties of these different types of matrices. This one is a square matrix. So we're going to denote this by I or by IN. So we'll look at that. All right. So here you might have some different products here. What would be the product of A times a 3 by 3 identity matrix? Can anybody guess on this one? Or can anybody make any conclusions as to why they might be written in this order? Based on what you know.
Are you asking why there's one diagonal?
Yeah, so why? So here they say if A is any M by N matrix, then A times the identity matrix here equals A. Or there's this other situation over here where I with a dimension of M times A equals A. Why would they have written it like that?
Are IN and IM 2 different matrices?
Yeah, so if we look at this first one, it's in this format. Does anybody know why the I is coming second? Can anybody guess?
So it can still be defined.
Yes, good job. Yeah, so for this one, so keep in mind if A is any M by N matrix, in this case, you're going to be multiplying this identity matrix after the fact such that this product can actually be defined. In this case, you'll be multiplying the identity matrix up front because that would be the way in which that product would be defined. Oops, sorry, I meant this to be an N, M by N. So do you guys see that? So here, this is a what? A 3 by 3? And this is what? This is a 2 by 3. So here, the 3's will match up. What if I had put this matrix in front? Would it have been defined? No. So keep that in mind. So you're going to want to look at this very closely. So when you have an M by N matrix, you can multiply it by an identity matrix with of size n by n, but the order will have to be that I comes second in order to get the resulting matrix A. And if you have an identity matrix up front, its dimensions are going to be m by m, and it's going to come in front in order for it to be defined.
So the reason it's highlighted that is essentially to say, kind of focus on the opposite, how like you can't have a times I to the m.
Yeah, so you would not be, this would not be defined. Like I to the n times a would not equal a. And a times I to the m would not equal a, because order matters, right? So keep in mind, when you have a matrix A that has m by n dimensions, in order to multiply it by an identity matrix and still end up with A itself, you'd have to follow these rules. That's interesting here. Yeah. So Nahar says the diagonals have 1 and the rest is zeros. Yes, that was true for our identity matrices. So keep that in mind. This is something that takes a little moment to think about. But this will only hold true if this is written in this order. For A to be multiplied by an identity matrix and still equal A, that I will need to have an n by n dimensions to be written in this order. For it to be written in this order, this identity matrix will need to have dimensions m by m. Okay, so here's the other thing that you'll want to look at is theorem 1.4.3. If R is the reduced row echelon form of a matrix, of an n by n matrix, then either R has a row of zeros or R is the identity matrix In. So you're going to either get to a situation if you notice here, if you have a square matrix A and you have gone through your reduced row echelon elementary row operations, you're either going to end up with this reduced row echelon form. It's either going to have a row of zeros or it's going to end up being the identity matrix In. So keep that in mind as well. So what is this for? Here's where you got to be really paying close attention to these theorems, because sometimes you're going to miss details if you're not paying close attention. So for this one, this said here for any matrix A that was m by n. So this one didn't necessarily have to be a square matrix. For this particular theorem, it's telling you that the matrix A is an n by n. So you want to always be very careful of these dimensions sometimes that they give you. Because it's going to tell you, does it hold for square matrices or does it hold for all matrices? So that's one thing to keep in mind. Okay, so then we are going to look at inverse matrices. So we consider, here's our definition 1. If A is a square matrix, and if matrix B of the same size can be found, such that AB equals BA equals I, then A is said to be invertible. So here is your one exception here, because remember we always said order mattered, right? If we're doing A times B, doesn't always equal B times A. But here, if you come across the situation where if you do the product AB, if that equals the product of BA, it is going to equal your identity matrix. And it's going to be said that A is invertible. So if this will hold true, A will be invertible. It's also called non-singular. And B is going to be the inverse of A. So if we can find that matrix where this is going to hold true, then A is said to be singular. Oh, sorry, if no such matrix B can be found, and then it said that A is singular. So if we can find an inverse, that means that that matrix A is non-singular. If it does not have an inverse, then it's going to be a singular matrix. So here we're going to be actually learning about the inverses. So here, this is where you would want to be able to prove to yourself where this happens to hold true. So in this instance, you should find, if it's an invertible matrix, we should find out that the product of AB is going to equal BA, and then those are both going to equal an identity matrix. So we are looking at example 5 here. So if we have AB, we're going to be doing it in this order. And we've got 2, -1, -5, 3. And then we've got our B here. We got 3, 1, 5, 2. So all that jazz. What do we got? We got 6 minus 5. That's going to be 1, right? So 2 times 3 plus -5 times 1. That's going to be 6 minus 5. Then we've got 2 times 5. That's 10 plus -5 times 2. Well, that's going to be 0 because that's 10 minus 10. Then what do we got? Then we've got -1 times 3. So that's -3 plus 3. That's going to be 0, right? Then we've got -1 times 5. That's -5. Plus 3 times 2, that's 6. So -5 plus 6 is going to give us a 1. So this is going to be your identity matrix here. Then we've got B times A. We'll just do that. We know that's one's going to be the same, end up being the same result. So 3, 5, 2. If we wrote this the other way. So in this particular situation, these are both going to yield the identity matrix. And we could say that B is going to be an inverse of A. So this would be your one exception, right? Because otherwise, order matters when you're doing multiplication. Yes.
Ignoring the negatives, are A and B transposes of each other?
So we're going to look at that. Are A and B transposes? So what do you think? What's our definition of transpose? What would be the transpose of A? Do we remember how to do that?
Oh, 2, -1, -5.
So AT would equal 2, -5. We put the columns and interchange our columns and rows. And we have 2, or -1, and 3 here. So to answer your question, what do you think?
Yeah.
Yeah. But we still want to know how to do a transpose because there are going to be properties that involve our inverses and our transposes. So keep that thought in mind. So it's a good thought. Okay. So here we have, can an invertible matrix have more than one inverse? Here's another thing you're going to want to commit to memory. No, if it's an invertible matrix, it has exactly one inverse. So you know how before we had reduced row echelon form and we said, well, there could be many many row echelon forms leading up to that point. But in this case, there is only one inverse for an invertible matrix. So that leads to this theorem. If B and C are both inverses of the matrix A, then that's going to mean that B equals C, because that matrix A can only have one inverse. So here, there's some other properties that A times its inverse is going to equal the identity matrix. And the inverse of A times A is also going to equal the identity matrix. So keep that in mind. All right. Also, here is something to not be confused about because you don't want to mix up your different forms of mathematics. Just realize if you see A here to the -1, that is going to mean the inverse. It does not mean 1 over A. So we're dealing with matrices. A lot of times people forget that. So just realize that's not going to be the case here. Okay, moving all along. So here is where we get to figure out how do we actually determine the properties of inverses. So we're actually going to calculate the inverse of a matrix and find a really easy way to do it. So if you have, this is a theorem you're going to want to bookmark. It's going to be on your study guide. Here, it says if you have this matrix A and here you have these entries, we're going to represent them by letters. It is going to be invertible if and only if A times D minus B times C does not equal 0. So if you're given a matrix that looks like this, you would quickly want to calculate, does A times D minus B times C, does it equal 0 or not? So if it doesn't equal 0, guess what that means? You have, that matrix is invertible. If it does equal 0, it means it's not, right? So this is a really quick test that you would want to do, is does AD minus BC, does that equal 0 or not? That's going to give you an answer. So it's going to save you work, right? You can quickly look at that and you realize that it does not equal 0. Well, you're going to be, well, I got to figure out then what the inverse actually is. If you find that AD minus BC does equal 0, then you would simply say, guess what? That matrix does not have an inverse. I don't need to do any more work. There's no way for me to find it out.
So if it equals 0, it's invertible.
If it does not equal 0, it is invertible. So if it does not equal 0, it is invertible. If it does equal 0, then it will not have an inverse. So here I'll go ahead and write it out just to be clear. So if AD minus BC does not equal 0, that means that A is invertible. There will be an inverse that you can calculate. If AD minus BC does equal 0, no inverse can be found. So hopefully that makes it a little bit clearer. So if we can figure out quickly that AD minus BC doesn't equal 0, we know it will have an inverse, and A is invertible, then we're going to be able to find that inverse of A quickly with this equation. So keep in mind that this is how we're going to note the inverse of A. So it's going to be A, and it looks like it's raised to the power of -1, but just keep in mind that's not exactly what it means. So this is how we denote an inverse. So for this matrix A that we originally got, we can figure out what its inverse is by doing this equation. So we divide 1 by AD minus BC. So you can quickly see why if that quantity AD minus BC had equals 0, you could see that that would be an undefined equation, right? So since we know it doesn't equal 0 and it is invertible, you're going to be able to calculate that quantity. The other thing that you're going to be doing here, if you notice, is that you're going to be switching the positions of A and D. So now A is down in this right corner, D went up to the left corner, and then B and C are each going to be they're going to have their signs reversed. So by calculating all of this, you're going to be able to find the inverse of A. Now, just one other thing definition-wise, this quantity AD minus BC, that is called the determinant of A, if you just calculate that. Because that's going to determine for you whether or not your matrix is invertible or not. So they call that the determinant of A, and that's going to equal your quantity AD minus BC. Keep in mind what I've just showed you is we're working with extremely simple matrices. So if you're observant and you saw this part of the slide, this is how you would calculate the determinant and how you calculate the inverse of a 2x2 matrix A.
So that only works for 2x2.
Yeah, so that's going to be specifically for your 2x2. We're going to have to do something different for our bigger matrices. So you'll get to see what that is. So this is a 2x2. Also keep in mind, what's another thing is it is also square. So these are all little hints that if you see a matrix, you should be able to immediately recognize what you can and can't do with it. So here's where we're going to start really writing these things down for each of them. Okay, so then we've got, all right, so let's try it. Okay, so we've got a 2x2 matrix here. We're going to be able to figure out, so what is going to be the determinant of A? How would we quickly do that? AD minus BC equals what? 6 times 2 minus our 1 times 5, which is going to equal what? 7. What can we determine immediately? Yes, A is invertible. So it has an inverse that we can calculate. Okay?
So you just did the 6 times the 2 across and 5 times the 1.
Yep, so this would be the A position, this would be the D position, this would be the B position, and that's the C position. So I did AD minus B times C. And what's going to be our inverse of A? So we're going to have 1 over 7 times what's going to go in there? -1, -5, and 6. And so then you'd multiply that out, and what would you actually get? Yeah, you get be something kind of ugly, right? 2 7s, minus 1 7. You got minus 5 7ths, and you got 6 7ths. That would be the final scenario there. So within, this was part A here. Then if we did part B, you'd be able to do that same thing really quickly. So who can do that one really quickly?
6 -6 plus 6 0, so it's not inverted.
All right. So this is AD minus BC. So here we have 6 minus 6 equals 0. Ooh, we do not like that. So that means no inverse. There's nothing more we can do. We're just going to stop. We're going to say A is not invertible. Can't find it. Well, this was part B, but they named this same matrix A as well. So the matrix A in part B. The determinant equals 0, so we knew immediately there's no inverse. All right. So here is some other properties that you are going to want to know. Woo. So the next thing is if A and B are invertible matrices of the same size, so here we've got 2 invertible matrices, and they're the same size, then AB is invertible. And so here, this is where it gets interesting. So you got to make sure that you kind of take care of this notation here. So here, the inverse of the product AB is going to equal the inverse of B times the inverse of A. So notice the order here. So this will only hold true if A and B are invertible matrices with the same size, then their product will be invertible as well. And you can determine what it will be according to this equation, but just realize it has to be in this particular order. So if you notice here, the inverse of B is listed first here on the other side of the equation. So it says a product of any number of invertible matrices is invertible, and the inverse product, and the inverse of the product is the product of the inverses in the reverse order. So here you can see B came first over here before A. So keep that in mind. So from here on out, this is really going to test your attention to detail with all these different theorems to be able to determine what can you do with these matrices. Okay, so we've got example 9, the inverse of a product. So here, if you would like to go through example 1-9, this is basically proving that that is so. So here you would do the product of A times B, and then you would take, so that would be inside the parentheses, then you would determine the inverse, and you get some sort of invertible matrix there. And then on the other side, you would go ahead and take the inverse of B, and then you'd multiply it by the inverse of A, and you should come out with the same answer for those. So I challenge you to kind of go through example 9 on your own and see that that is true for yourself. So here are just some other different things that you're going to want to know. I think this kind of is similar to some other things you've probably seen before. But A to the 0 power here, that is going to be your identity matrix. Here we do similar things where if A is raised to a power, you basically multiply that A by itself, however high n is. So here you have negative integers of the powers of A. Here's a little bit where you might want to really look at this. So keep in mind here, when you have A is raised to a negative power, what you're going to want to do is you're going to want to pull out the inverse first. So if you notice here, you're pulling out the inverse of A, then you're multiplying the inverse by how high your factors are, by n factors. So does everybody kind of see that? It's a little bit different than maybe what you're used to. So A to the nth power is pretty kind of obvious. You've done that before in other types of maths. You got matrix A times A, however many it goes. Here, when you're faced with a negative integer, you would want to pull out the inverse. Here it is in parentheses. And then whatever that inverse is, then you would take it out to however n factors. Here, if you're faced with, you have A to the R times A to the S, here you would have a simple addition. Here you'd have a simple multiplication. So these are rules worth looking at. So I would basically recommend to you guys, so I'm providing you with a study guide, is I would have all your theorems kind of lumped together so you can have them for quick reference. And the things that you really want to take note of is you've got to look at the order of things. You've got to look at like what size matrix are they talking about, because that is where your attention to detail is going to be crucial. So here are some other different theorem rules here. So if A, so they say if A is invertible and n is a non-negative integer, then the inverse of A is invertible, and then the inverse of A is going to go back to A. So you can kind of see where they're going with this one. Here, if an is invertible, and A to the n, and then the inverse of that is going to equal here this quantity, and then here where you've gone ahead and pulled out the inverse and then used your factor. Here you've got a scalar k. You can see how this can be manipulated. This is going to be important. Here they've taken the product of Ka first, then taken the inverse. That we kind of see again from that rule I shared with you before. That is going to equal the product, but here you can see where they've taken each inverse individually. We are going to look at where A to n is invertible, and the inverse of A to n is going to equal these things. We're going to prove that to ourselves. So here, let's suppose that we have A to the -3. Ooh, what are we going to do? So if you're faced with this, if you remember from what I've said before, you're going to want to pull out the inverse. So you'd have A, the inverse of A, and then that will be to the power of 3. So here, this is going to equal this inverse of A matrix 3 times. So that's going to be everything we get here.
So that's 41 times 11.
11 times 41
Minus 30 times 15.
minus 30 times 15.
All that multiplied by 41.
All that multiplied by what? Yep.
Negative 30.
Whoop, yep, 30. Or wait, would it be 30?
Negative.
Got negative 30? Okay. Then what?
Negative 15.
Okay.
11.
And 11. And that should get you what? What does this quantity equal? A to the 3, that one would be, we've kind of skipped some steps, so let me get them in here. So if you did A3 to the 3 first, so you'd have like 1, 1, 2, 3, and that'd be 1, 1, 2, 3 times 1, 1, 2, 3. So you get that matrix, and then you would take the inverse. So that one, if you're doing out all of those 3 together, ooh, I'm running out of space. This one was 11, 30, and then 15, and then 41 would be the answer to that. And then determining the inverse from that, you can see where the A and the D got switched here to put that there. And then the 30 and the 15 now have negatives. And then you're multiplying it by the determinant. Yeah, I should have gone through and like done this step for everybody, but it's kind of hard to fit all on one slide. Like here, like usually when we think of numbers raised to the negative power, we think of them being equal to 1 over A. But just realize we're working with matrices, so that's not what that means in this instance. These are pretty simple to go ahead and prove as well. So here, if you have the transpose of A and then you take the transpose of that, you should get back to your original matrix A. Here, if you take the sum of A and B and then take the transpose, that's going to equal the transpose of A plus the transpose of B. Same with that subtraction. Here, when you're working with a scalar times a matrix, you can multiply that scalar K times the matrix first and then takes the transpose, or you could take the transpose of A and then multiply that by K. Then here's the one, though, that you're going to want to pay attention to the order. So once again, for this last property E, the product of A times B, and then you take the transpose, that is going to equal the transpose of B times the transpose of A. So please note this one has an order that you need to pay attention to. So the transpose of a product of any number of matrices is the product of the transposes in reverse order. So we saw that as well with what other? So there's some things where order does matter in a lot of different instances, especially with your transposes here at the end. So we're going to go, I know there's a lot of definitions in this one, but you're going to want to make sure that you go through this particular section carefully. And you're going to want to accumulate all of your theorems.